Type of energy called elastic energy, and of course this is the energy of well, simply an elastic band, right? You stretch an elastic band, there's energy in that band, right? And once you release that band, the thing goes flying, right? So that would be an example of elastic energy. So it's a new type of energy we haven't applied to before, but we're going to apply it. We're going to add it to our conservation of energy equation. It's going to be fun. Okay, but first looking at the equation for it. If I drew a graph, forget elastics for a minute, and if I drew a graph of someone pushing a piano down the hall, say over a distance of 5 meters, and they're using a constant force, and I want to measure force and distance, right? I have a graph where I'm doing force and distance. So it's a constant force of 2,000 newtons, and the distance is 5 meters, and so if I made this into a graph, which maybe I would for some reason, I don't know. Then, and I calculated the area under that graph, it would be the length, which is, excuse me, the 2,000 newtons. Say that was length, and this is width, times width, is the area under the graph. Little fun fact coming up, if you do the calculus enrichment, and if you don't do the calculus enrichment, you'll learn it in first year, well, physics, but calculus, is that the area under a graph is integration. So that term integration, this is something really Sir Isaac Newton made up to find the area under a graph. Now, of course, on a graph like this, he didn't have to work very hard, right? Because it's just a rectangle. But you can imagine the reason why he had to do this is, what if the force, and specifically he was working with gravity, right? But what if the force was something that it wasn't a linear, it wasn't just a straight graph like this or just a triangle or something. What if it was some curvy graph and he wanted to find the work, so to speak, done? Well, he had to figure out a way to do that, and he invented integration to do just that. He invented derivatives, which is the first what you learn in high school calculus, so that he could find slope or rate of change anytime. And he invented integration to find the area. So while this seems like a lame exercise, I'm just introducing you to the practice of integration. Anyway, so in this case, though, the point is that the area under this is 1,000 Newton meters, which is 1,000 joules, which is the work, right? It's all the same thing. And, you know, work and energy are sort of synonymous. So if we take something that you may have done last year, I introduced the spring force last year, and I did show you earlier in the last lesson the idea that if you had spring force, and I give it the subscript x, because I've run out of subscripts. I think that the textbook uses, oh, I don't know, might use E, I can't remember, it might use S, but S is for static friction, E is for energy, electric energy. So anyway, I use X. And say you're stretching a spring a distance of 1 meter, and that takes 200 newtons. You might remember that the graph generally looks like this. The more you stretch it, the more force it takes, right? So now you have a triangular system. And if I want to find the energy stored in that spring, which is really the work needed to be done to stretch it that far, I can still do this because it's just a regular shape. I don't need to use integration, right? Now it's a triangle, so it's 1/2 base times height, where the base is a meter and the height is 200 newtons, right? So then if I'm looking at spring energy or elastic energy, if I use the terms one for the other, they're the same thing, spring energy, elastic energy. It's going to be 1/2, in this case I wrote height first, but Fx times x, which is the stretch, right? In the spring, we call the amount of stretch x, and that's so 1/2 kxx, replacing fx with kx, which we learned in the last note. And that gives us the equation. This is what you have to know. Okay, that the elastic energy or spring energy stored in a spring or elastic system when it's stretched a certain amount is equal to 1/2 times kx squared. How much it's stretched squared times k, which is the spring constant. Okay, so this is the equation. This is the important thing to get out of it. All this stuff will help you understand it better. I'm not going to put it on a test, I can't imagine. But you will be learning integration soon. Okay, so here's the details then. The deets. Excuse me. The symbol, we're going to give the symbol for elastic energy or spring energy, same thing, as EX. The unit, like every other type of energy, is joules. There's our formula. And this is the K is newtons per meter, and X has to be meters. Okay? and it is the potential for it to move. So your lab, the first lab you're going to do, I think is, I actually stole the idea from, one of my colleagues in Godrich told me he did this. I thought, what a great lab. You take a spring, not an elastic, but actually a spring. You figure out the K value for it. You have to do that on your own, figure it out yourself. You stretch it a certain amount on an angle, then you let it go, and using the idea of projectile motion, once you know the K value, you should be able to predict where the thing's going to land. So I guess I'm saying it backwards, because what you do in the lab is first find the K value, decide on an angle, it can be just 45 degrees or whatever, but you're going to launch that spring on an angle. You should be able to calculate where it's going to land. Then take a piece of sidewalk chalk or whatever, go outside, make a circle to say this is where the thing's going to land, or put a box or something to say I'm predicting it's going to land here. You're going to step back, launch it, see if it lands there, and then talk about the reasons why it didn't. Last semester, I think there was a couple kids who got it in. Okay, it's possible, but there's lots of error, of course. But anyways, that's your lab next time. So you do the calculations first, similar to the circular motion lab. You do the calculations first, and then you'll try the lab and see how close you are. I'm looking forward to it. Maybe you're not, but I am. Anyway, here's just an example. I have a couple examples. I'll probably do them all in this video. I might break off after this one because it might get long. But here we're saying a child's toy shoots a rubber dart of this mass. First of all, I want to apologize, but this is my picture of the child's toy, just because I couldn't find one better. Okay, so what it is, you compress a spring inside of the toy, and then you place the dart, it's like where the mass is. Okay, so then I have a spring, I compress it to this point. Okay, I know the K value, and I know the mass M of my dart. And it says the spring is initially compressed 4.5 centimeters and it's horizontal. Okay, so there's my compressed factor, right? And the idea is that when this toy releases, what happens is, when you hit the trigger or whatever, the spring releases. And once the spring is not stretched anymore, when x equals 0, it's like the dart still has speed, right? And that's why it leaves the toy, and it's got momentum, right? It's not locked in position, it's free to move. So these two things are not connected right there. Okay, so it's asking us to determine the speed of the dart when it leaves the toy. Well, first of all, almost every single time I give you a spring question, it's going to be conservation of energy. Very rarely will we apply, do like in the last set of questions where we sometimes find accelerations and that. You can, but if it's asking for speed, it's going to be conservation of energy. So we do it twice. One where we have no friction in the system, and that by friction I just mean between, say, the dart and the surface of the toy, which would be between M and the surface right here. And in the second one there is some friction. Okay, so it's the same question twice, just once we add thermal energy, right? So let's look at the first time. Here's how it changes. Now we have a new type of energy, so we just add it to either side. Okay, add elastic energy to each side of the equation. I add EX1 and EX2 for initial and final. So the total energy at the beginning equals total energy at the end. Before you continue, you might want to step back and say, okay, what's the energy transformation here? Well, we're saying there's no thermal, so there's no energy, heat loss, and the thing's horizontal, so the gravitational is all 0. Really, we're just taking some elastic energy, we're releasing the elastic, and it's turning into speed, to kinetic energy. Okay, so height does not change, so all the EGs are 0. EX2 is 0 because we're saying the toy, this is just something you would know. I wouldn't necessarily put that down in the question, but it's implied without any other information that the toy is released when x equals 0. The second x is going to be 0 at the equilibrium position. And we're told in part 1 anyway, part A, that there's no thermal energy. Okay, so here's really what happens. Okay, so then I can just put in the formulas for them. I'm solving for V2. The halves cancel because they're 1 on each side, right? And just cancel those out. Cross it out, and rearrange for V2. Sub in your numbers. So the thing that the dart leaves the toy, it's a pretty reasonable number of 9.5 meters per second. Okay. So you might want to get all that down. But there's the data for the question. You might want to get all that down and then pause it. I'm just going to move on to the friction one, okay? And you should see the friction won't change it very much, right? It just is another little way to make it harder, okay? So pause if you need to. I'm moving on. So second question, almost exactly the same, but now our energy transformation is elastic energy becomes kinetic and a little bit of heat loss. Okay? Notice the way I'm doing this, I'm not subbing in numbers till the very end. So here's my data. I know my K, I know my X1, I know my mass. This time I have a mu K, and I know my distance. The delta D, like for E thermal here, is FK delta D. And E thermal then is mg. Because FK, you should know this by now, that FK is normal times mu K. So normal in this case, it's just straight up and down, right? So it's just mg. So this is the normal force. This is mu K, and that's delta D. Okay, that's where this is all coming from for E thermal. So the delta D part is just, it happens to be the same as X because it's the distance of contact, right? So that's all the stuff I know. Looking at the formula then, you're probably writing this anyway, but I'm saying I start with just elastics. That's just the 1/2 kx1 squared equals the kinetic energy, and then there's my thermal energy. Okay? So I want to find V2. So see how I rearranged that? I got V2. I just brought this over here, and I just made it. So my kinetic energy then is my elastic subtract the thermal, right? Just looking at this again. If I want this by itself, it's going to be EX1 minus E thermal, right? That's all this step tells me. And rearrange and solve for V2. It's a lot, and I know that rearranging is part of the skill you need to work on, but it's not the part I'm teaching you, so that's why I'm jumping ahead quick. If you have trouble with this rearranging, of course, you can ask me, but I'm just going to assume that you can at least trust me that this is correct for now, and then when you do your own questions, you might have to work through some of the details. Okay? Anyways, look at that mouthful. But the neat thing to get out of this, look at the answer. Look how close the answer is to the question from before. I have a 0.3 kinetic coefficient for friction coefficient, and it's 0.01 meter per second slower. That's why I had to keep so many decimal places, just to show you that, by the way. So this is why often when we say friction's insignificant, I mean it really is, right? It's not that we're just being lazy or trying to make the questions easier. Sometimes it makes all the difference, and sometimes it means essentially zero difference, right? Okay, so I know that you might need to pause to get that down, but I'm going to jump to the next example and just keep it as one long video, okay? Example 2. Oh, no, I'm not, because I have to fix that. So we'll just stop there, okay? I'm going to pause it and make a new video.